Hey, you should be able to see my screen now. Nutrient application, critical concepts, is that correct?
Yes.
Okay. Yesterday, I had the opportunity to present the concepts of nutrient management planning at a pretty high altitude. And today, this talk on nutrient application, critical concepts, is really kind of a follow-up to the idea of planning, because it's my contention that planning is essential, documentation is essential, but really that is secondary to what you actually do in the field, because it's what you do in the field that really makes a difference in terms of your production or your protection or your addressing of various concerns. So really today is really trying to move from the paperwork aspects into the real world practical aspects of nutrient applications and nutrient planning. The other thing that, to be honest, I'm a little uneasy with this presentation, because normally this presentation that I'm giving today is broken into two completely separate presentations, and each one will run anywhere from 35 to 45 minutes if I'm working at it carefully. Otherwise, it'll run even longer. So I'm going to be a challenge to present the concepts here, which means I'm going to be covering at a pretty high altitude and providing brief summary, but I've got a couple of places where I'll provide links for pursuing additional information. And of course, you'll notice that on the lower right-hand side of the screen, I've got my email address and my phone numbers, and I'll be available throughout this workshop and into the future if you have questions. With that, let's go ahead and begin. See if we can get this going here. Okay, the first thing I'd like to present is the idea that the soils, from a practical perspective, can be thought of as a bathtub, where you have a certain level of nutrients that are in the soil that are available to the plants. Now, this is a gross oversimplification of the biology and the chemistry taking place in the soil, but it's effective from a day-to-day management perspective. And the idea is you really want to maintain that fertility within acceptable levels of fertility available, but also acceptable levels of risk. And normally I'm talking about environmental losses to the water and potentially air. So when you're thinking of the soils as a bathtub, you really have a spigot that you're pouring nutrients into that soil, and that may come from inorganic fertilizer, it may come from organic fertilizer. And the key concept we need to remember is NP and K is NP and K regardless of what the source is. However, the source will play a role in its physical characteristics and how it handles or possibly smells if you're talking about animal manures, or possibly the number or amount of potential pathogens or biological activity associated with the product. On the other end of the bathtub, you'll see that we're actually removing nutrients from the soil through our crop production component. From a nutrient planning perspective, at least with manure applications in the past, there's been a tendency to say, okay, let's supply the nitrogen needs of the crop and not really think about what the phosphorus application rates are going to be or the potassium rate applications are going to be. But when you look at the major nutrients needed by the crop of NP and K, you really need to be thinking about, there's an application rate that optimizes for nitrogen. There's one that optimizes for potassium. There's one that optimizes for phosphorus. But really, if you're trying to manage your resources, you're trying to get a balancing act going there. So you hit a crop sweet spot where you meet the needs of all three without oversupplying any of the other two. And I did a lot of talking yesterday about phosphorus index planning. And really all that's doing is writing your nutrient management plans that are base are on that nitrogen to phosphorus side of the triangle. So realistically, from a nutrient management planning process, you need to be thinking about your nitrogen, phosphorus, and potassium. But you need to think about more than that as well. You need to be thinking about what the soil moisture is, because without the moisture, your plants are not going to grow. You need to be thinking about what is the soil pH, and we'll see some slides in a minute that point to the importance of soil pH and its potential implications for the need for lime. Micronutrients is an issue that we need to be thinking about with our nutrient planning. And under the last point I have over there is soil biology. We're hearing a lot of emphasis being put on now about soil health. I'm not smart enough to know exactly what soil health is or how you exactly measure soil health, but I am smart enough to know that that involves soil biology, the microorganisms, the environment within the soil, and there's a lot of biology and biochemistry involved with there. So we need to be thinking about that with our applications as well. Now with our fertilizer nutrients, soil testing is the best way to get a handle on what's in the soil. And once we know what's in the soil and what we need for the crop that we're trying to grow, that will help us get a handle on how much to apply and what sources of nutrients to apply. And as indicated just a moment ago, we're really looking primarily at nitrogen, phosphorus, and potassium. And the soil test results really report what's in the soil. Now, a question that comes up real often with soil testing, excuse me, is, well, how do you soil test? What are you trying to do with your soil test? And the short answer is what you're trying to do is for every acre of ground or the field or area of interest, you're trying to end up with about 2 cups of soil that represents what's in the top 6 inches or top 4 inches of that soil in the field. So how do you do that? You have to do that by sampling. And as you see on the screen here, one approach to it is you just zigzag across the field and you get enough spots that you get a representative sample of the whole field. You try to avoid the hot spots or the boggy spots. You're trying to collect samples that represent the whole field. And then you composite those samples so that you get a physical averaging of the field. If you want more detail and you're trying to do a diagnostics of where are the fertility zones in the field, that's a case where you may want to go in and do grid sampling, and then you get your sample results back from the grid, and then you have the chore of taking the mathematical numbers and doing a mathematical average or creating maps of the NP and K concentrations of your field. And that's, I would argue that that's not the routine way for your normal management. The normal management is zigzag the field, collect a physical average to be sent to the lab. When you submit your samples to the lab, what you're really trying to do is develop that representative sample that I just talked about. So what that means is you want to sample an area that you're going to manage the same way. You know, if you're sampling an entire field and you're going to treat the whole field the same way, you might, collect one soil sample. However, if that field has got a hillside and a bottomland and you treat those separately, you probably want to cut that field apart and sample them as separate areas of management. I can see this concept going so far that if you're working in a horticultural setting and you're growing tomatoes in one area and string beans in another area, you may want to separate out your sampling so you're collecting samples for those 2 different areas. When you go through and you're collecting your samples, you'll collect multiple subsamples and you blend them together to create the composite for your management area. That composite of soil will need to go to the lab, but don't send it to the lab in a wet form because it becomes a physical pain in the neck. They're shipped in cardboard boxes. One of the best approaches I've seen a person use for sampling is she would go off and collect her soil samples and do in a pans, mix it in the bucket, put the bucket into a gallon Ziploc bag, label it, and leave it open till she got to the office. Then she'd take what was in the plastic Ziploc bag, put it into a paper lunch bag, and then just put those on a shelf to air dry for a couple of days, because you don't want to dry them in the oven. You don't want to microwave them because that changes the soil chemistry, and it's liable to change the results on your soil test. Because what we're doing with the soil sampling for this process is we're not measuring the total amount of phosphorus and potassium in the sample. What we're trying to estimate is the amount that's available for the crop. And those are two different sets of numbers. So when you get your sample ready to go, you take it to your county extension office. And here in Arkansas anyway, the basic soil tests are free because they're paid for by a fertilizer tax. Additional testing is available for small fees. At the bottom of the screen, you'll see a website for the Mariana Soil Testing Laboratory, and that provides more details on the Arkansas recommendations for soil testing process. Also provides a link to where our county offices are, so that you can contact them and procure sample boxes. Now, yesterday I was reminded that we have some folks on in the audience who are not from Arkansas. My recommendation for you would be what I've said here is generally correct. Get in touch with your local county extension office and say, hey, I'm interested in the details of soil sampling, and they'll be happy to help you. You get your test results back, and there's going to be a lot of information in there, and it'll be on a form. You may need some help from the county agent for interpretation of what those are. One of the key components on the soil test results to get back is what the soil pH is of that soil. And for background on general chemistry, going back to our high school chemistry, you'll recall that a pH of 7 is neutral. As the number goes below 7, it gets more acidic. And as it goes above 7, it gets more alkaline and more basic. And the thing that's a little tough to keep up with or remember is when we go from a neutral soil of 7 to a pH of 6, it is actually 10 times as acidic. So it's a log function. And in Arkansas, our typical soils will run in the 4 to 7 range. Other states where they tend to have more calcareous soils, volcanoes, ocean bottom, that kind of stuff, the pH will tend to be higher. Now, why is pH important? We can see here from this slide that different types of plants like pH ranges to be a little bit different. The grasses are labeled as needing 5.7 to 7, whereas the boxwood is 5.5 to 6.0. So the crop that you're growing will have a pH range that it really likes for its soil to be in. But there's another reason why pH is important. This slide may look a little bit scary, but really the way to interpret this is on the bottom, we've got our pH range running from 4 to 9. And for the various nutrients, nitrogen, phosphorus, potassium, also bacteria, and on down, you'll see that the width of that bar changes. Well, when it's narrow, the nutrient is it's relatively unavailable. Where it gets thick, it becomes more available. That means that for nitrogen, if you're down in the 4.5 range, you can have a lot of nitrogen in that soil, in total nitrogen, but the available nitrogen will be much less. So that kind of helps point to why pH adjustments become important to make the nutrients that you apply available for the plant, because You can keep putting out fertilizer, but if it's not available to the plant, you're not getting a return on your investment for that fertilizer application. So really what we're doing is we're going through and we're soil sampling to figure out what's in the soil, and through that collective representative sample. And then we're going to try to match what's available in the soil to what is being supplied by your fertilizer or your soil amendment, so that you get a good match or a good connection. So when you get your soil samples back, you need to review your soil sample test results. You're looking at what are the P2O5 and K2O recommendations. And notice I've shifted from NP and K to P2O5 and K2O, because when we're talking about fertilizer applications, we're really talking about the oxide forms of potassium and phosphorus. The soil test results will also give an indication of whether lime is needed to be added or not, to make sure that the nutrients applied become available to the crop. If you got a special case going, there may make some recommendations for micronutrients. And at least in Arkansas, and I suspect the other states as well, at the bottom of the page, there'll be some extra notes that pertain to the timing of the application, whether you make the application all at one time or you split it into multiple applications. And there may be some recommendations in terms of the method of application. Do you broadcast it over the whole field, or do you strip it down right next to the roots of the plant? And when you go to figuring out which nutrients you're going to, fertilizer sources you're going to apply, you really need to be thinking about, what are my sources of nutrients? What are all the recommendations? And we also need to realize that, just like yesterday when I was talking about the planning process is kind of a juggling act, and you weren't going to get the puzzle pieces to fit together just right. You'd have to bend some tabs, make some compromises. The same is going to be true with meeting the recommendations for the fertilizer. Kind of a classic example in Arkansas is our fertilizer recommendations are expressed in terms of applying inorganic fertilizers. Well, when you're applying a animal manure, it's a pre-blended fertilizer that typically the value of the fertilizer and the application rates are such that you really can't it's not convenient to make split applications multiple times over the year, because you got to clean out the barn. So you end up having to kind of balance the practical aspects of your application with the technical aspects of the soil test recommendation. With organic materials, so far I've been talking primarily with inorganic fertilizers, but with organic fertilizers such as poultry litter or barnyard or compost, they are a very good source of nitrogen, phosphorus, and potassium. Effectively, they are pre-blended sources of nutrients, just like you can go to the hardware store and pick up a bag of triple 13, where you can go get 100 pounds of animal manure and it'll have its blend of nutrients. It will also have, as we discussed yesterday, micronutrients and some biological components that need to be considered. The organic materials have some real advantages in terms of providing for soil till and helping provide microorganisms to the soil to convert nutrients into forms that plants can utilize. Here in Arkansas, we've got one classic example of the advantages of an animal manure. When you land level a field to improve the irrigation, you have the possibility of removing so much topsoil that you get past the topsoil into the subsoil and you lose the fertility of the topsoil. Well, an application of a couple tons of chicken litter to that will get your fertility back in a year versus decade of commercial fertilizer applications. On the other hand, organic materials also may be a source of undesirable, but I would argue manageable pathogens. And we'll have other presentations to discuss that. The nutrient NP and K ratios often don't match the crop need ratios. There's a mismatch between what the crop needs and what the manure or the organic matter supplies. So the way to approach handling that, or the way I would recommend doing it with an organic based material as an application, is use the organic fertilizer, test it to see what's in there, and then you can use the amount of nutrients supplied by the organic fertilizer can be extracted from the soil test recommendation. Then the differences can be used to go back in and add commercial fertilizers, typically nitrogen, to meet all of the crop needs for N, P, and K without exceeding one of those too much. And this should be calculated as part of a nutrient budget and nutrient management plan, even if it's not a formal plan, even if it's something that you're doing on for your own use. These calculations and budgeting, I'd recommend that you use. If you need to have a sample collected, analyzed, the Fayetteville Agricultural Diagnostics Laboratory is good. The website's there. You can go to commercial labs, but they're not going to be near as cost competitive as the university lab. And also the university lab is used to providing the analysis in a way that is consistent with the land-grant universities across the nation. It participates in quality testing programs to assure that. In summary, so far, we need to remember to soil test to determine the amount of plant nutrients we need. We need to remember to test our organic materials so we know how much nutrients are in them. And we need to select our nutrient sources and the amounts we apply so that we're matching as closely as we can the fertilizer recommendations as closely as possible. Now, I will be the first to admit that one of the beauties of inorganic fertilizers are they are a very consistent product. The labeling on the bag will tell you what's in there. With organic materials, your consistency is way down, the variability goes up. So it makes it more of a challenge. And we need to realize that with the use of organic materials, we're really looking at long-term averages. So 1 year may be off a little bit, but over the long term is really where we need to be thinking in terms of our management. Okay, so far what we've talked about yesterday was bookkeeping, paperwork, planning. This talk we've talked about, okay, testing and caliber and doing the calculations on determining how much to apply. Well, the next question is, okay, I know how much to apply and I know how much, and that tells me how much I want to apply, but how do I guarantee that I'm going to apply the amount I said I'm going to apply or that I want to apply? Because doing all the paperwork, doing all the calculations doesn't mean anything unless you can actually apply what you want to apply. So calibration is really bridging that gap between the desired and the actual. Now, there are two aspects of nutrient applications, and therefore calibration needs to address these aspects. And that's one of the rate of how much is being applied. And the second is the uniformity, how even is it supplied? And what you can see on the right-hand side of the screen is my rather poor attempt to try to depict a gearbox. And in that gearbox, it only works when the gears mesh upright and you got all the gears in place. And so for nutrient applications, we're really looking at one gear being uniformity, the other being the rate, and both of them need to be addressed. So as I indicated, rate is how much, usually expressed in tons per acre or pounds per square feet. If you're working in the small pots, it may be so many ounces per pot. You've got to figure out what your units need to be. And then on the uniformity, it's really a case of how much does it vary across the field, or how much does it vary down the row if you're applying by a row, or maybe if you're applying to multiple pots, are you applying the same amount of material to each pot? And in the field, it's pretty easy to see when something goes haywire, because you can drive by the field and you can see nice green areas, and you'll see areas where it looks burned. So you get a lot of streaking. That makes it easy to take a look at what went wrong, kind of after the fact. I suspect the same is possible if we're working with pots or down the row. Now, the other thing we have to remember when we're dealing with uniformity is with our applications, with some applicators, you actually want to, they apply more in the middle and less as you get farther out, and that rate will run from high to low for each pass. So you want to make the passes close enough together so that you get a nice uniform rate as depicted in the center across the field average. But if you get it too close together, you start piling up your application rates, and it gets more than you want it to be. Now, if your application method is something like a drop spreader where you're dropping it straight down and your distribution is 0, jumps to whatever your rate is, comes across and drops down, your overlap needs to be very small. So really, it's kind of a Goldilocks situation. You can go too wide, too narrow, or just right. And that determination of too wide, too narrow, just right will really depend on what piece of equipment you're using and how the application is being made. And with those, I would suggest either referring back to your equipment manuals or getting in touch with the appropriate county agents. Okay. Now, how do you assess uniformity? Well, I just described one method of assessment a minute ago, and that's looking at your field afterward and say, well, does that field uniform the green, or do I have big green streaks and yellow growth areas? So, looking at what you did in the past can be used as an assessment method. Of course, you can't fix what you've done in the past, but maybe you can avoid it in the future with a change in practice. Now, when you're determining your application rate, here's where, frankly, I struggle. And I don't struggle over the concepts or the approach. What I struggle over is the sheer number of different ways that you can actually make your applications. I normally struggle with the fact you may be spreading with a liquid honey wagon, or it may be a big gun irrigation system, or it may be a poultry litter spreader truck, or it may be a regular manure spreader truck, maybe a landscaper who's spraying a chemical out of a hose. Adding to all that variability, yesterday we saw in our virtual tour, an application method was dig a hole, take a shovelful, put it in a hole, and put the soil back and mix it up. Valid, great way to apply nutrients right where they're needed. But does present another method or another question about, okay, well, how do you judge how much you're putting out? Is it the right amount at the right place? And that really goes back to the details of each application. But the basic concepts for determining your application rate boil down to either what I call the load area method, which is taking a known amount of material and you apply to an unknown area, or a weight area method, which is you take an unknown weight, but you're applying to a known area. Hopefully the examples will fit a little better. With the load area method, or as I said, known amount applied to an unknown area, you can see the steps there. I'm going to skip through those steps because I'm running short on time. But you can see those steps, and what you end up with is you end up with a rate, which is a weight per area result. The weight area method is that unknown weight applied to a known area. Typically, you apply to a tarp or something, and you end up at the same number of rate is equal to the weight of material applied per area. In summary, calibration bridges that target rate to the actual rate that you're trying to achieve. The application, we need to think in terms of rate, which is how much, and uniformity, how even. And on top of that, during the application, we need to think about what time it needs to be applied. And you've got the two different application methods that you're going to possibly use. And really, both of them will end up at your rate, which is the amount per area. Any questions? I think I've got a couple of minutes left.
We do have one